Hey everybody, Mr. Murray's Mathland here, and today we're talking about critical points in calculus. And before we find the critical points for this function, let's talk a minute about what the definition of a critical point is. So a critical point is a value c such that f prime of c is equal to 0 or f prime of c is undefined. So any x value where the derivative is 0 or undefined, and it should be said that c must be in the domain of f of x. So the function itself does exist. To be considered a critical point. So for example, that would rule out where a vertical asymptote might be, or a hole in the graph. Now they might be sort of critical in the sense that they're important. There's strange stuff going on there, but that's not in the definition of what's called a critical value or a critical point or a critical number. Sometimes you see those terms used interchangeably. So and this really just refers to the x value, even though it says critical point. Usually you think x and y coordinate. So that's what we're looking for here. So basically anywhere where the derivative is 0 or undefined. Now this function right here, if you'll notice, the domain is all real numbers. That x to the 2/3, that's like taking the cube root of x squared. The cube root is always defined, whether it's positives or negatives, does not matter. So the domain is all real numbers here. Our derivative should be pretty easy to find. It's a straight power rule. So 2/3 times 12, that's going to give you 2/3 times 18 is going to give you 12. Sorry, I was jumping ahead a step. X to the negative 1/3. Don't forget to subtract 1 from that exponent. Minus 4. And we'll move that down to the bottom there. You could call it the cube root or keep it as x to the 1/3. Does not matter, but there is your derivative. And right off the bat, hopefully, you can see that, hey, f prime is undefined at x equals 0, because that's what makes that denominator 0, and that of course is going to make this fraction undefined, which means f prime is undefined, even though f is defined at 0. So that's one critical number right off the bat, x equals 0. And now the other variety is, where is this derivative equal to 0? So we set the function equal to 0. You know, sometimes that can be a tough thing to solve. Sometimes it's, easy. And this is one of the more doable ones here. So you're cross multiplying or basically just swapping these places here. That 12 over 4 is equal to x to the 1/3. Or 3 is equal to the cube root of x. And so, of course, to solve that, we're going to cube each side, and we get 27. So we have two critical numbers here, and one of each of the variety. One place where f prime was undefined, one place where f prime was 0. Doesn't really matter. You don't have to classify when they ask for critical points. So 0 and 27. But I thought I'd bring in the graph just so we can see, some reminders of what makes a derivative 0 versus what makes a derivative be undefined. So we bring in this graph here, and this is the graph of f of x equals 18x to the 2/3 minus 4x. And so you can see on this graph, at x equals 0, there is a cusp, there's a sharp turn in the graph there, and that's one of the ways that a derivative can be undefined. The other way is at a vertical tangent line, like on a cube root graph, or any place where the graph itself is undefined. The derivative obviously wouldn't exist. So that's definitely a classic situation. You got a cusp there. The function exists, but the derivative does not at that one sharp turn. And the place where the derivative was 0, as you can see, and that should be making sense, is that maximum there at x equals 27. That's a nice smooth spot where the slope is 0 on that graph. So okay, so some nice to tie together the visual of what you're looking at with what you're finding algebraically. So hopefully this makes it clear. Got any questions? Just let me know.